Hi, I'm Lucy, and I'm totally not a robot. In a few previous videos, I've started building this breadboard computer, based on the Intel 8086 microprocessor. So far, I've added plenty of debug LEDs, a clock that I can single-step, and I've managed to demultiplex the shared bus, so that I can access the address on the left, and the data on the right, at the same time. And if you remember, I did that because I want to connect a ROM chip, that I'll hopefully be able to use to store a program. But as I've mentioned in the previous video, even with the bus split, there are still a few things that I need to figure out. And hopefully I'll be able to sort everything out in a single video, so let's get right to it. This is the ROM chip in question, the 8028C256. Let's start by plugging it into the breadboard. With that done, let's have a quick look at the datasheet. The chip has 8 data pins, in this case labeled I/O0 through I/O7, and I've intentionally oriented the chip on the breadboard in a way that these face towards the data bus. But here's the next problem. The ROM chip only has 8 data pins, but the data bus on the 8086 is 16 bits, so what can I do about that? I suppose I could try to find a ROM chip with 16 data pins. These do exist, but are not very popular and relatively hard to get. A much easier way to tackle this is to simply use another 8028C256 and wire the two together, so that one always provides the upper 8 bits, and the other one the lower 8. This, of course, will make the wiring a little more complicated, but I think in the end it'll be alright. So as usual, let's start by connecting power and ground to each of the chips. Next, let's have a look at the WE, or write enable pin. The obvious question that you should ask is that since this is a ROM, or read-only memory, why does it have a write enable pin at all? And the short answer is that this particular chip is an EEPROM, or Energy Erasable Programmable ROM, which means it is in fact possible to erase and reprogram the contents. And I'll be doing that a lot, trying to run different programs, but I'll use an external programmer for the writing. From the point of view of the computer, the contents will indeed be read-only, so I can safely tie both write enable pins high. The OE, or output enable pin, is the exact opposite. It indicates that data should be read from the ROM chip. So I'll tie both of those low, as I want the chips to always output data when they're active. And I say when they're active, because it's not enough to just bring the OE pin low. Looking at the datasheet, it is clear that in order to read data from the chip, both OE and CE pins must go low. The CE, or chip enable pin, is used to determine whether the microprocessor, or in fact anything else on the bus, is even trying to talk to the chip. So how do we determine that? This is where things are finally starting to get interesting. Each of the ROM chips has a capacity of 256 kilobits, or 32 kilobytes, so the two together add up to 64 kilobytes. With its 20-bit address bus, the 8086 is able to address 1 megabyte of memory, so we need to reserve 64 kilobytes of that space for the ROM, and build a circuit that will activate the chip enable signal on the ROM chips when the address is in the correct range. Fortunately, 64 kilobytes is not a bad number to work with. It's exactly 16 bits, which makes the math and wiring a tiny bit easier. I really don't want to make this more complicated than it has to be, and I think the most sensible thing will be to use the bottom 16 address bits for the ROM chips. Which means I only need to figure out what to do with the upper 4 bits. And that's actually pretty straightforward, because I want the entry point address, FFFF0, to fall into the ROM, and that has all the 4 upper bits high. So I think that enabling the ROM chips only when the upper 4 address bits are high is exactly what I'm looking for. And as a bonus, if I look at the address as 5 hex digits, the upper 4 bits form the first digit, which means that all the addresses starting with F will fall into the ROM, which is nice and easy to remember. But it's not that simple. Let's actually start writing it down. So I want the top 4 address bits high, that's A16 through A19. And I understand this pseudocode notation is probably not the most correct one, but it works for me. For simplicity, I'll call the result of this conjunction F, simply because it represents the F at the beginning of the address. Next, I'll define a helper signal called common, because it'll represent the part of the chip enable logic that is common for both ROM chips. The first thing that I want to do is to make sure that the ROM chips don't activate when ALE is high, because at that moment it's the 8086 that drives the bus, and having multiple things driving the bus at the same time is not a very good idea. Then, if you remember, in some of the previous videos, I've mentioned that the 8086 has 2 separate address spaces, one for memory, and the other one for I/O. And as the name, read-only memory, suggests, the ROM should only activate for memory addresses, which means the MIO signal must be high. And of course I also need the F signal, so I'll throw that in as well. Which wraps up the common part, and at this point I can no longer ignore the fact that there are in fact 2 separate chips. Another thing that I've mentioned in a previous video is that though the data bus is 16 bits wide, these are in fact 2 separate 8-bit buses working together. Each half can be enabled and disabled separately, and if you remember, one of the pins on the 8086 is BHE, or bus high enable. And surprise surprise, this is what indicates whether the high part of the bus should be enabled or not. So I'll have to define 2 separate chip enable signals, and since I'm already at it, let's start with the one that enables the high half of the bus. Of course, I need all the common bits, and then I'll also throw in BHE, or in fact BHE inverted, because the signal is active low. Now the lower part of the bus. Again, I'll need all the common stuff, but unfortunately I have no such thing as bus low enable anywhere. Luckily, the 8086 datasheet explains this, in a slightly cryptic way, but it does nevertheless. You can clearly see in this table that while BHE controls the upper half of the bus, it's A0, or the lowest address bit, that controls the lower part. And at first glance, this is super confusing, as it seems that A0 serves 2 purposes at the same time. It's a significant digit in the address, as well as a control signal for the lower part of the bus. So if you think about it, that means that all the odd addresses will have the lower part of the bus disabled. And it took me a fair amount of time to absorb this, but that's exactly how it works. See, the 8086 being a 16-bit microprocessor, reads data in sequences of 16 bits, or 2 bytes. Which means that the A0 signal is in fact irrelevant for the address, because the upper 19 address bits are just enough to clearly identify 2 bytes of data. The A0 signal then only decides whether the lower byte should be transferred on the bus or not. But wait, that's still stupid, right? Wouldn't that mean that the odd addresses are kind of second-class citizens, only operating at half the potential? And that's exactly how it is. You might have noticed that during execution, the 8086 only jumps through even addresses. It starts at FFFF0, then goes to FFFF2, FFFF4, and so on. But what you must understand is that this is one of the first 16-bit microprocessors, and when it launched, most peripherals were still only capable of 8-bit transfers. So having a simple way to downgrade to 8-bit mode is actually kind of a big deal. In fact, it's a feature, enabling compatibility with all the 8-bit hardware out there, without the need of any special hacks. And with that explained, let's go back to my chip enable signals. Now I know that for the lower chip, I need to replace BHE inverted by A0 inverted. And that's almost it. The logic seems correct, but the chip enable signal itself is active low, so I'll actually need to invert each of them. Perfect, but I need to build this in hardware, and I don't immediately see how to do that, so let's use a little Boolean math and see where we get. First, I'll get rid of the outer inversion. Next, I'll expand the common signal, as defined above. Then, just for better visibility, I'll tie the ALE inverted and MIO together, which is okay for a conjunction. And finally, I'll get rid of the outer inversion. I know this only looks half done. I could continue and flatten everything to just disjunctions, but I'll actually keep it in this form, because it looks like something that I'll be able to build in hardware. Especially the first element, ALE inverted and MIO, all of that inverted, looks rather scary. But it's in fact just two NAND gates, one for inverting ALE, and the other one for combining it with MIO. The F-inverted signal can easily be implemented by a single quad-input NAND gate, and the rest, BHE and A0, I can just use as they are. Then of course I'll need a few OR gates to combine everything together, but that shouldn't be a problem. So enough theory, let's start building. I'll start with the F signal, for which I'll need a quad-input NAND gate. And guess what? Here I have a 74HCT20, which contains a couple of those. Looking at the pinout, it should be pretty straightforward, one gate on each side, with 4 inputs, and 1 output. There's also a couple pins labeled NC, which stands for not connected, and that basically means I should not touch either of them at all. And with that, let's plug the chip into the breadboard, somewhere close to the upper 4 address lanes. Then of course, connect power and ground. And next I'll connect A16, A17, A18, and A19 to the 4 inputs of the top NAND gate, keeping in mind that I need to skip the NC pin in the middle. Beautiful, and just like that, I now have the F-inverted signal available on the upper right pin of the chip. And since I'm not using the bottom NAND gate, as usual, it's good practice to tie its inputs to predefined values, so that there are no floating pins that could cause trouble. Let me just quickly connect all of them to 5 volts. And that's it for this chip. Next I'll have a look at the signal that combines ALE inverted and MIO. For that, I'll use the 74HCT00 chip, which provides 4 dual input NAND gates. Once again, pretty straightforward, a couple gates on each side, each with 2 inputs, and 1 output. I'll add it here, right next to the address latches, and I do realize that on camera, it'll probably be partially hidden under the red and green address bus wires, but I'll do my best to make as much visible as possible. First I'll connect power and ground, and it looks like I might need to move the capacitor on the power rail out of the way, at least temporarily. With that done, I'll start by building the ALE inverted signal. And for that, I'll use the fact that you can turn a NAND gate into an inverter if you connect the same signal to both of its inputs. If you remember, I'm using the ALE signal to trigger the address latches, so I don't need to route it all the way from the 8086, I can easily access it right here, from the bottom left pin of the latch. To make wiring simpler, I'll use the bottom left NAND gate for the inverter. Let me quickly uncover it. First, I'll tie the 2 inputs together, and then I'll also connect the ALE signal to one of them. And that gives me the ALE inverted signal right here, on the output of the NAND gate. Next, I need to connect it to one of the inputs of the next NAND gate. And just like that, the last remaining thing is to connect the MIO signal to the other input. Unfortunately, unlike the ALE signal, I have no shortcuts to access the MIO signal, so I'll have to route it all the way from the top. And with that in place, the output of the second NAND gate should be exactly what I need, ALE inverted and MIO, all of that inverted. Which means I should have all the bits necessary for the final step. BHE is available here, on the top bit of the address latch, then I have the ALE and MIO combined on the output of this NAND gate, F inverted is right here, and A0 is on the address bus. I'll just quickly tie the inputs of the two unused NAND gates high, so that the outputs don't float, and then I can add the 74HCT32 chip, providing 4 OR gates. Its pinout is identical to the previous one, 2 gates on each side, each with a couple inputs and a single output. I'll plug it in right here, next to the ROM chips, because it's the outputs of these gates that will provide the chip enable signals. And as you can see, sometimes the chips fight back, especially when they are brand new. You need to kind of massage them into the breadboard. Hopefully I didn't break anything. And you already know the drill, power and ground goes first. Let's now go back to my calculations and see how I need to combine everything. And I think the most sensible way to tackle this is to start by combining the ALE-MIO signal with F inverted. That will produce a helper signal, which coincidentally is labeled common inverted, just a few lines above. Then I'll be able to combine that signal with BHE for one of the chips, and with A0 for the other chip. Let's get to it. I'll use the upper right OR gate for the helper signal, and I'll start by connecting the combination of ALE and MIO to one of its inputs. When done, this is what it looks like. Then I'll bring the F-inverted signal to the other input of the OR gate. There it goes, not the most elegant, but it works. And so on the output of this gate, I have a signal that combines the top 4 address bits, ALE and MIO. And now I'm just one step away from building the actual chip enable signals. I'll start with the right ROM chip, and I'll use the top left OR gate for the wiring. I'll connect one of the inputs to the helper signal, and the other one to A0. And that's it, right here, at the output of the OR gate, is the chip enable signal, for the ROM chip connected to the lower part of the data bus. For me, that's the one on the right, so let me finally connect its CE pin to the CE low signal. Well, that'll do. Now I need to do the same for the other ROM chip, and I think I'll use the bottom right OR gate for it. So first I need to bring the helper signal down, which might be tricky. It requires somewhat precise bending of short wires, so let's see how it goes. Okay, my first grey wire was a little too short, but this orange one should do fine. Now I need to connect the BHE signal to the other input of the OR gate. And honestly, I have no idea why my past me had decided to do this right now, but before connecting the BHE signal, I'll tie the inputs of the last unused OR gate low, so that the output doesn't float. But now, back to the BHE signal. I have it latched together with the address, here in the top bit of the left latch chip. Let me quickly route it down. Yeah, that'll do, so that's the CE high signal. All that remains is to connect the output of the OR gate to the CE pin of the left ROM chip. So that's the chip enable signals dealt with. All that remains is to connect the address and data pins to the respective buses. But not so fast, I want to take a slight detour and add a little bit more debugging. Here I have an LED bulb, and I know that I've mentioned many times that I don't like to use them, so feel free to throw that in my face. But this is a weird, 3-legged LED, which indicates that it might be multicolor. And indeed, this particular one can glow red or green, and the way it works is that the middle pin is a common anode, so it goes to 5 volts through a resistor, and depending on which of the 2 remaining pins is brought to ground, the bulb glows either red or green. Let's shorten the legs and plug it into the breadboard. And guess what? Here's another one. As I've mentioned, the middle pin should go to 5 volts through a resistor, so let's do that. What I'm trying to build is a visual indication of when each chip is accessing the bus, so that I can at any moment see who is writing data to the bus and who is reading it. And of course I need the two colors to distinguish between reads and writes, so I'll use red for devices that are putting data on the bus, and green for devices reading it. So how do I decide whether the ROM chips are putting anything on the bus? That's simple. I've already seen that in the datasheet, both CE and OE pins must be low. It does also say that WE must be high, but I've unconditionally tied that high for now, so I don't need to care about that. And now I need to build a circuit that goes low when CE and OE are also low, and otherwise stays high. But hey, that's an OR gate, right? So let's call another 74 HCT32 to the rescue. And you guessed it, 5 volts and ground first. With that done, I think it is reasonable to use the 2 gates on the left for the left chip, and the 2 gates on the right for the right chip. And when I say 2, I'll actually use both. One will be active when CE and OE are low, which means the chip is writing data on the bus, and the LED should be red, while the other will be active when CE and WE are low, which means the chip is reading data from the bus, and the LED should be green. Of course, the latter is impossible right now, as I've permanently tied WE high, but who knows, maybe I'll want runtime updates in the future. I'll do the left side first, and I'll start by bringing the CE signal to one of the inputs of the bottom left OR gate. Next, I'll bring the same CE signal to one of the inputs of the upper left OR gate. Then I'll connect the OE signal to the other input of the bottom left gate. And oops, it looks like I'm actually off by 1 with the CE signal. Let me quickly fix that. Good, and now back to OE. With that connected, the output of the bottom left gate should have the trigger for the red light on the left. Let's continue by connecting the WE signal to the remaining input on the upper left gate. Nice, and now let's finish by connecting each gate's output to one of the legs on the LED. And if you're wondering how I know which leg is which color, I really don't. But what I do know is that in this configuration the LEDs can only glow red, so if I turn the computer on, and it glows green, it's the other way around and I'll simply flip it. So here I have the output of the bottom left OR gate, going to the left leg of the LED. And similarly, the output of the upper left OR gate, going to the right leg of the LED. So that's the left side dealt with. Now I need to do the exact same thing on the right side, and since there is no difference and I think this was boring enough, I'll just speed through it and show you the result. Beautiful, isn't it? But I still want to do the same with the other player on the bus, the 8086 itself. I'll add another LED right next to it, and run the middle pin to 5 volts through a resistor. As for the red and green legs, I don't want to overcomplicate it, and I'll simply use the read and write signals from the microprocessor. You'll see in a bit that it's not a perfect solution, but it'll do for now. Just like that, I have the read signal connected. Now let's do write. And that's it, this should work. But I think that's enough debuggers. Let's go back to the ROM chips. The only thing remaining is wiring the address and data pins, and I've intentionally left this to be the last step, simply because there is no nice way to do this. The pins on the ROM chips themselves are not aligned nicely, and wiring them will inevitably create a spaghetti of wires. So let's do that. I'll start with the data pins, which in my case are on the right side of each chip. I'll start with the right ROM chip, and the lower part of the data bus. Pins 0, 1, and 2 are on the bottom side of the chip, and the rest, 3 to 7, are on the top. So just like that, the bottom half of the data bus is ready. Let's do the same with the upper half. And that's done as well. I understand it's not very well visible on camera, so what I did is that I've connected pins IO0 to IO7 from the right ROM chip, to pins D0 to D7 on the data bus, and similarly pins IO0 to IO7 from the left ROM chip, to pins D8 to D15 on the data bus. What remains is the address pins. We have to keep in mind that A0 is used to enable and disable the lower part of the data bus, and we should not include it in the address. So everything is shifted by 1, pins A1 to A15 on the address bus, connect to pins A0 to A14 on the ROM chips. I'll start with the left ROM chip, and again, there is no nice way to do this, as the address pins are kind of scattered around in random order. Well, that should wrap up the left ROM chip. Now, for the right one, it is not necessary to reach all the way left to the address bus. Since the address pins are shared between the two chips, we can simply connect the respective address pins on both together. And with that done, everything should be ready for a test run. I doubt I did everything right on first try, but let's connect power and see what happens. So immediately, as you can see, the LED next to the left ROM chip is green, which, as I said, should not be happening. But right now, the computer has not been reset yet, so it's in an undefined state. Let's run through the reset sequence and give it a chance to recover. So as usual, 4 clock pulses while holding the reset button, followed by 7 more clock pulses after releasing it. And you might have noticed that the read and write signals on the 8086 are neither high nor low now, but I'll talk about that in a little bit. So here we are, right after reset. The 8086 is putting address FFFF0 on the bus, and what is concerning is that the LED next to the left ROM chip is still bright green, which suggests some problem with wiring. But let's step the clock 1 pulse further and see what changes. Now the 8086 is clearly issuing a read, and the LED next to the ROM chips should only glow red, so it looks like all the LEDs are in fact connected the other way around and need to be flipped. There, much better. The other ROM LED seems to be glowing green all the time, regardless of the inputs, so I'll indeed have to check the wiring. It also seems that my MIO indicator is not working, as the signal should be high now. But let's do a few more clock pulses to see what else is broken. And so far it seems to be doing all right. The working ROM chip disables during T1 when ALE is high, which is exactly what it should do. Let's speed up a bit until the point where everything breaks. Yes, here it is. So now the 8086 is issuing a write to a random address, and the ROM chip is correctly disabled. So I think that's enough for now. Let me disconnect the power and figure out what's wrong with the left ROM's LED.
A few moments later.
Okay, so even my camera couldn't watch me struggle and overheated, but in the end I was able to figure it out. The problem was with this chip, one of the OR gates was always outputting low, regardless of the inputs. And you might remember me struggling to get it into the breadboard earlier in the video, so it's likely that I've unintentionally broken some contact while doing that. Nevertheless, I've replaced it, and here I have the broken one, so let's get rid of that, and we're ready to run another test. And while I'll run through the reset sequence, I can say a few words about the read and write signals, which are sometimes neither high nor low. This happens when both signals are driven low, in which case the LED tries to glow both red and green at the same time, and apparently allows some current to flow in the opposite direction. But that only happens before the first reset, when the whole system is in an undefined state, so I don't care too much. Here, as you can see, once the system is properly reset, everything seems to be working. All my new bus LEDs are off during T1, then during T2, the 8086 LED turns green, while both ROM LEDs turn red. Nothing changes during T3, and as the 8086 stops reading during T4, its LED goes back off, even though the ROM chips still output the data on the bus. Sadly, I've only noticed that the MIO signal was broken while editing the video, so I'll have to fix that one off the record. There is one notable change though. Instead of having all zeros on the data bus when nothing is driving it, with the ROM chips in charge, I'm getting all ones. Let's step the clock forward and see if the behavior changes. And here we are. So now the 8086 is issuing a write, so its bus LED turned red, and it's writing to address 0FFFE, which means the ROM chips are inactive. But wait, 0FFFE is the same address as before, so it seems that it makes no difference to have all zeros or all ones on the bus. That's weird. These should be different instructions, so the behavior should be different, right? Well, yes and no. If I remember correctly, the last few opcodes do not represent any instructions, so it's hard to say what happens when they are executed. Let's actually quickly try that. I'll create a file containing 6 bytes, FA to FF, and then disassemble it. And indeed, FA through FD are the last valid opcodes, while FE and FF are labeled DB, which stands for data byte. So that's still not very useful, and I bet that if I pulse the clock a few times, we'll get back on track. And there we go indeed, and that's where I'll end this video. I've finally added a somewhat interesting circuitry. The ROM chips are now wired, and they even seem to be working. I know the amount of debugging that I keep adding might seem like an overkill, but hey, it helped me identify a broken chip, which would be pain to debug later. So it looks like that in the next video, finally, I'll have a look at building my first program, writing it to the ROM chips, and actually running it on this very computer. Woohoo!